Hello. In this lecture, I will be covering the topic of rotations of rigid bodies. The subject contains several subtopics: the center of mass, torque, moment of inertia, and angular momentum. So I'm going to cover each of them in this lecture. We begin with the center of mass. But before I do that, I want to define for you what is meant by a rigid body. When we say rigid body, what we mean by that is that, as you know, bodies are made out of, say, atoms and molecules. A rigid body means is that the interatomic or the intermolecular distance between the molecules that make up the body do not change. Okay? For example, liquid water is not a rigid body because the intermolecular distance between the H2O molecules changes because it's just the nature of the liquid water. It's fluid. Okay, but for a rigid body, say a piece of copper or a piece of iron, a solid piece of iron, it's rigid because the interatomic or the intermolecular distance between the constituents that make up the body are constant. They don't change. Okay, and that's the definition of it. Again, keep in mind that those definitions go back to the 19th or 18th century, where back in those days people did not yet knew what a molecule is and what an atom is and so on. So let me begin with the center of mass. So any rigid body has a center of mass. What is a center of mass? A center of mass is the following. If I have a rigid body, say for example a stick, okay, and if I would let's say I would have the stick or this rigid body to rotate freely, unconstrained, and with no net forces on it, what will happen is that it will rotate about its own center of mass, about its own specific point where what we call the center of mass. Let me explain. Suppose I have a wrench, okay? A wrench looks something like that. I'll try to graph it or draw it. It's not very pretty. Hold on. Something like that, okay? And there's a hole here. So the wrench's center of mass, let's suppose it's about here. I'm going to put an X with a circle on it. So this is where the center of mass of the wrench, okay? If I would take it, suppose that this is the ground and here I am, and I'm holding the wrench in my hand, okay? And suppose I'm going to throw it as a projectile. So it's going to go up, up, up like this and then down here like that. So what's going to happen now? Of course, as I throw it, I'm going to have it rotate. So let's suppose that the wrench would rotate something like this. It will be, as it is moving along the trajectory, it's also rotating. Well, it's rotating about the center of mass. Okay, something like that. Okay. In other words, if I would, let's say, go back to this wrench right here and go back to the point of the center of mass, and if I would pay attention to the center of mass point as that wrench is following this parabolic trajectory, I will find that the center of mass will be exactly located at all time on the parabola as the wrench is spinning about it or rotating about it. You understand that? Like that. Okay? So that's basically what it is. So the center of mass of this wrench, it basically will be exactly on the parabolic path, the trajectory, like that, as the wrench's body is spinning about it in however direction. Okay? Why is that? Because that's the nature of the center of mass. The center of mass is when an object rotates freely, unconstrained, and with no net forces on it, it will rotate about the center of mass. Okay, that would be one definition for it. And there is a formula that allows you to calculate the center of mass for simple systems. I'm going to write them down and I'll give you some examples. So the formula, so the rotation about the center of mass, I'm going to say cm, center of mass, and there are 2 points for the center of mass. One in the x coordinate, one has the point, assume it's in the plane, xy plane, so they will have an x and y coordinate. That's what I'm trying to say. So for the x coordinate, it's going to be 1 over m, and then the sum of m sub I x sub I. And for y sub cm, the y coordinate is 1 over m. Let me just write it down and explain it to you. And this is the summation I over I of m sub I y sub I. What does that mean? The meaning is the following. Suppose I have, let me go to the book and I'll show you an example. Right here. So we have here, imagine you have what looks like a dumbbell like that. There we go. A barbell, he calls it. Let's say you have a barbell. Let me make it magnified and just show it to you right here. So you get two masses, and then you have a rod in between them like that. And this mass is 2 kilograms. This mass is 0.5 kilogram. And this mass is located at 0.5, on the x-axis rather, at 0.5 meters, and this one is at the origin, or at 0, okay? And there's the center mass right here. But let's suppose that we want to find the center mass, the location, the exact location of the center mass, okay? So it says here, a barbell consists of a 0.5 kilogram ball and a 2 kilogram ball connected by a massless 50 centimeter long rod, okay? So we're going to ignore the mass of the rod because it says massless. Where is the location of the center mass? That's the first question. And what is the speed of each ball if they rotate about the center of mass at 40 RPM, revolution per minute? I hope you remember that from a previous lecture. We covered rotational motion. So how do we do something like this? Well, again, we go back to that. Let me move this on the side like here. There it is. Okay, so the way we do it is, let me write down what's given to us. I'm going to draw the, as well also the barbell. So you have one mass here and a smaller one here. This is 2, this is 1. The center mass is somewhere here. Then we have the x-axis right there. That's the x-axis, and he said this is x equals 0, given to us. And the ball number 2, I'm going to call that x1, x2. I'm going to call that x1, and this is x2 equals 0.5 meter, okay? And I want to know the location of the center of mass, which is right somewhere. Where is it, okay? The location of the center of mass. Okay, so how do we do it? Well, here is the formula. This is for the x-coordinate. This is for the y-coordinate. As you can see, this one is just along the x-axis, so we're going to ignore the y-coordinates. I'll give you another example where we're going to use the y and x-coordinate. But for the x-coordinate, let me rewrite the coordinate formula in a different way. What that means, if I have two masses here, look at that, I only got two masses, right? So here he says the sum of the mass 1 times the location of mass 1 plus the m2, x2, and so on. So I can write it this way, m1, x1 plus m2, x2 over the big M here is basically the total mass of the entire system. The mass of ball 1, mass of ball 2, and the mass of the rod. Okay, he said the rod is massless, but basically you want to add up all the masses. So that's basically the meaning of it. So it's going to be M1 plus M2. M1 plus M2. There we go. Of course, the same thing applies for the y-coordinate, so it's just going to be M1 Y1 plus M2 Y2 plus M3 Y3, however you have, how many number of masses you have, and then m1 plus m2 plus m3 and so on, instead of saying like that. Okay, so let's apply that for our case. So in this case, the center of mass, I'm going to call it x sub cm. That's going to be, again, I'm going to use the formula. Let me just bring this one down right there. So I'm going to write the data as you look at this formula right here, guys. So that's going to be the m1 here is 2 kilogram. So that's going to be 2 times the location of it is 0, correct? x1 is 0, plus the mass m2 is half times half. Times half divided by the total mass. The total mass is going to be 2 plus half, correct? That's going to be 2 plus 0.5. And then we calculate that. As you can see, this is 0 right here. So, and when we calculate, it becomes 0.1 meters. Okay. So basically, if I go back to my the diagram right here, this center of mass right here is at the 0.1 meter mark. You see what I'm saying? That's basically what it is. And of course, it doesn't have a y coordinate because it's all along the x-axis. So basically, if I want to write down the center of mass point, maybe we can call it r center of mass like that, which basically means x sub cm comma y sub cm. That's just one way of denoting it. So that would be something like 0.1 comma 0. Okay, that'd be one way to write it down. All right. Okay, here's one for my notes. I don't have one here. Let me just make up one. Let's make it 3 dimensions, all right? Suppose I have xy axis. So here is the x-axis, excuse me, the y-axis. Here is the x-axis. And let's say I have a mass right here, and I have a mass right here, and let's say I have another mass. Pick anywhere you want it. Let's put it here, for example, right there. Let's make it small. So I'm going to call this mass number 1, mass number 2, mass number 3. I'm actually just in making up this problem as I go along. I don't have it in my notes. Okay, suppose that M3 is 3 kilo. Let's make it 1 kilogram. Okay, M3. Suppose M1. Let's make it 3 kilogram. And let's say M2, M3. Sorry, no, this is M1. What am I doing? M1. M1 is 3 kilogram. M3 is 1 kilogram. And M2, let's make it 2 kilogram. Okay. And let's suppose that the location of M1, let's say -2 on the x-axis. This is the x-axis right here. That's the y-axis. And let's say -2, of course not -2, 2 on the y-axis, okay? And let's suppose that M3 here, let's suppose that this is -3 and this is -1 right here. And let's suppose that mass 2 is located at, say, 3 meters, okay? All meters here. I hope this is all of this is clear. So now he's asking the question, where is the center of mass? Okay, of course the center of mass, if you kind of look at it, it's going to be somewhere in the middle, somewhere here. You know what I mean? The center of mass point. Okay. In other words, imagine that is a rod that connects 2 and 3 and 3 and 1 and 1 and 2, and then you would allow this rigid body to rotate freely in the air. So it's going to be rotating about one particular point, which is the center of mass point. Where would that point be? I don't know. Let's just suppose it's here somewhere. I don't know where. So we can actually calculate that very accurately. And the way we do it, we simply use the same formula that we use here. What is it? Right there. We're going to use those two formulas, okay? The only difference is that we're going to be using 3 masses, okay? So let's do it. So I'm going to start with x sub cm. I'll reach the edge of the screen. Let me go maybe down here. X sub cm. So I'm just going to go for it. So it's going to be like something like m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3, right? Is that clear? So then we can just put in all the numbers. So start with m1, and that's going to be 3. What is x1? Negative 2, right? Plus m2, and that will be 2 times x sub 2 is 3. Is that right? X sub 2 is right here, right? Plus M3 is 1 kilogram times x3 is equal to negative 1. Okay, divided by the total masses 1 plus 2 plus 3. So that's going to be equal to minus 6 plus 6 minus 1 over what? 6. So those cancel out. I end up with negative 1 over 6. Is that right? Let me convert it to decimal because I want to plot it on the xy plane. So that's going to be 0.17 roughly. So that's going to be roughly negative 0.17. Okay, there we go. This is basically x sub cm. Where is it located? Well, let me show you where. It's somewhere. This is negative 1. So this is negative 0.17 is somewhere right here, okay? Now I want to find the y coordinate for all of that. All right, so we're going to do exactly the same thing except for the y coordinate. Can I squeeze it here? Maybe I could squeeze it here. Okay, so it's going to be y sub cm. Let me just put all the numbers immediately. So it's going to be starting with 1 right here. So that's going to be 3 times 2 plus, for M2, this one right here, that's going to be 2 times 0, correct? Why 0? Because that is the y coordinate here is on the origin, right here, at the origin. And then plus, let me extend that a little bit. I can do that. There we go. Plus, that's going to be, the mass is 1 times negative 3. All of that divided by the same mass, which is 6, right? So let's calculate that. That's going to be 6 plus 0 minus 3 over 6. And that gives me 3 over 6, and that's half, or 0.5, if you will, meter. Okay? So now I have y sub cm is 0.5. In other words, my center of mass position vector, if you want to call it, that's going to be what? It's going to be something like negative 0.17i plus 0.5j. I hope you know this notation. We covered it already in a previous lecture. That will be the center of mass. Or I can write it as a point. The point would be something like that. You know, x sub cm comma y sub cm, and that will be equal to negative 0.17 comma 0.5. Now let me plot it, okay? So if I'm going to plot it, let me use a different color. And so that's negative 0.17 is roughly here, and half is roughly here. So basically the center of mass is right there. I'm going to make a big dot, and that will be the center of mass. Or rather, maybe I can go something like that. This is the center of mass right here. In other words, if I have this body connected with rods, massless rods, I can't do it. Those are, let's say, massless rods like that, And if I would take this whole body and spin it up in the air, okay, just, you know, spin it up in the air, what's going to happen is going to spin, is going to rotate about an axis that passes through the center of mass, and the center of mass is right there. Got it? That's the meaning of that. Okay. Okay, good. One more. Oh, I forgot to go back to the, sorry. I'm going to go back to the problem that I started, the example that I got from the book here. There is part B to it. I forgot, I would like to do it. So let's go back to that. It says, so what is the center of mass? We found the center of mass to be equal to, sorry, I forgot about that. Anyway, so the center of mass is 0.10 right here, right? And then the second part is interesting. He said, what is the speed of each ball if they rotate about the center of mass at 40 revolution per minute? Remember we talked about this one. So what is this 40 revolution per minute? And if you remember, I told you we can consider it to be frequency in the wrong unit. Remember, the frequency is always revolution per second or hertz, right? So you want to convert that to that. So that's basically, so let me just go back and just say, oops, let me change the color. Continue. So here we have the frequency is, I forgot it already, sorry. What is it? 40 RPM. So that would be 40 rev per min, correct? And I just delete the min and make it sec. So it's going to be 60 sec here when I replace it. So it's going to be 40 over 60 rev per sec. So that's 4 over 6, 2 divided by 3. That's 0.67. So that's going to be 0.67 hertz. There we go. That's the frequency. I'm going to write it down again. So all of that, oops. That's the frequency, okay? All right. So now he said, what is the speed of each ball? In other words, this ball is going this way, and this ball is going down, right? So suppose it's going this way. Suppose the speed of the ball if they rotate in the center mass. So he didn't specify clockwise or counterclockwise. Let's suppose it is counterclockwise, because counterclockwise is positive. Keep that in mind. The clockwise, the rotation of the second hand, or the hour hand, or the minute hand in a clock is always negative. Okay, always remember that. Okay, it's not just for this section, for this lecture. Always remember that. Even in engineering and all, the rotation of the clock is a negative rotation. Okay, keep that in mind. Counterclockwise. Clockwise. Clockwise is negative. Counterclockwise is positive. That's what it is. Because you want to follow the right-hand rule. Anyway, so suppose it is counterclockwise. So it's going to go up. This one is down. So it's going to go in this way. Suppose this is counterclockwise. All right. So he said, what is the velocity v here and here? Okay. Now remember, as they rotate freely, they're going to rotate about the center of mass, correct? So that means is that this is the radius of rotation for M2, and this is the radius of rotation for M1. You see what I'm saying? So going back, we say, okay, well, V, or V1 rather, is equal to, let's go back, let's review. We know that V is equal to what? Omega R, if you remember. The velocity. Okay, so if I'm going to draw this again, so here is the smaller mass, 2, and here's the bigger one. Is that how it looks like? Yeah. So this one is going, and that is the center of mass right here. So this one is going this way, okay? So that's, I'm going to call that V2, excuse me. And then this one going down this way, this is V1. This is R1, and this is R2, okay? So he's asking for the V1 and V2, okay? So V1 and V2, so V1 is going to be basically omega R1, and V2 is omega R2. If you remember, omega is constant or the same for any rotating body, okay? Regardless of the radius. The one that differs is the velocity, the linear velocity V, but omega as the system is going around like this. Okay, that's omega. You see what I'm saying? That omega is constant. So I need to find it. Well, that's why he gives me the frequency. So what is omega? The omega is 2 pi f. And I have it. F is given to me. There we go. Okay. Be careful. You never use the RPM. It always have to be in hertz. So you have to convert it into cycle per second. So we have here 2 pi times 0.67. That will give me the omega. So I can calculate that. So that's times 2 times 3.14. Answer. I got 4. Let's make it 4.2. So I have here 4.2 radians per second. Okay. Oop, omega. And now V1 is equal to R1 omega. So R1 is equal to, we have it in the problem right there, R1. And R1 is, we got it from this is the location of the center of mass. So from 0 to 0.5, and this location of the center of mass is 0.1, so R2 would be what? 0.4, right? Okay. So that's going to be, R1 is 0.1, which is basically the radius of the center of mass. And omega is 4.2, and then we calculate that, and that gives me 0.42, correct? Meters per second. Okay? What that means is that V1 is going around the center of mass like that. What's the speed? What's the tangential speed? 0.42. Now this one has a larger radius, and to catch up with it, it's probably going to be not probably, for sure, it's going to be faster. Okay? So now we can calculate V2, which is R2 omega. Back to the drawing. R2 is right here. Well, if this is from 0 to 0.5, and this is 0.1, so that must be 0.4, correct? So it's going to be 0.4 times omega is 4.2. 4.2. And that's equal to 4.2 times 0.4, answer 1.68, 1.7 roughly. 1.7 meters per second. So it's a lot faster because it has a larger radius. You got that? And there we go. That's how we do this problem. Okay, good. The next topic I want to talk about is conservation of energy. But here we have something new, and that is the whole topic is about bodies or rigid bodies that are rotating. So here we will have conservation of rotational kinetic energy. Okay. All right. Let me explain what that means. I'm going to make it a little bit shorter, and then I'm going to move it a little bit here. Okay, so rotational kinetic energy. I am not going to derive it. Please go back to the book and see how the rotational kinetic energy expression is derived. If I'm going to be deriving the torque equation and the rotational kinetic energy and moment of inertia and angular momentum, it's just going to be a whole extra hour over and beyond this video. So please go back to the book and see how it's derived. I'm just going to talk about it, explain it to you, and I'm going to show you how to use it in a problem. Okay, but please go back to the book and look at the derivation, how the formula, the expression for the rotational kinetic energy is derived. It's very simple, really, but it's important that you know it. All right, so I'm going to explain it to you conceptually. Here is the meaning of it. Suppose I have an inclined plane, say a ramp like this, okay? And suppose I have a box, I'm holding it here. Suppose that the ramp is smooth, okay? And I let it go. So it's going to slide down, right? So it's going to slide down until it hits the ground, whatever. Let's say until it comes here, all right? And suppose you know the height of it, h. And I ask you, what is the speed of the box, let's say, right before it, right before it reaches the bottom, right here, the velocity of it. Okay, so we can easily, and remember, we are saying that there is no friction. Okay, I'm taking it really, I'm making a very simple assumption here. So to use conservation of energy, as you know, at the top here, the total energy basically is potential energy, and that's equal to U equals mgh, right? I'm assuming you know all about it. We covered this in a previous lecture. The mass of the box, m, g times height, okay? At the bottom here, okay, assuming that there is no friction, well, all this potential energy has been converted into kinetic energy. And so the total energy here is basically kinetic energy is equal to 1/2 mv squared, right? And of course, when we say the total energy here is K plus U, so here K is 0, and this up here, right? K is 0, so you only got U, and that's equal to mgh. Here, however, we have E equals K plus U, but U is 0, because at the bottom, and there is no height, so it's all K, and that's equal to 1/2 mv squared. However, because of the conservation of energy, this E and this E are the same, and therefore mgh equals 1/2 mv squared. We're going to equate them together. And then you solve for whatever. You solve for the height or the velocity, whatever it is. And I'm sure you're familiar with all that. This is just a little review for you, okay? Now, as far as this chapter is concerned, what I'm going to do, I'm going to take the same example here, but this time I'm not going to have a box. I'm going to replace it with a wheel. Okay, let's replace it with a car wheel or whatever. So here is my ramp, and now I have, or a ball, if you will, whatever. Okay, so I have a wheel or a ball, and now I'm going to let it go. So I have at the height, same problem, it's a height h. And the ball at the bottom right here, and I'm being asked to find what is the velocity of the ball here at the bottom. Okay, like I said, it's identical problem. Okay, the only difference is geometry. Here I have a box squared. Here I have a ball or a wheel or a disc or a sphere or a ring or whatever, something rotates, and it is so it's going to go from here to here. Now, my question to you is, what's the difference between the two? In terms of, the mechanism, what's the difference between? You can pause the video and think about it. But the difference basically is the following. This box, it's sliding down until it hits the bottom. This one, it is also coming down, but at the same time it's spinning. In other words, here it has two motions. One is translational motion or linear motion in a straight line going down. That's the first motion. And the second one, it's spinning about this axis. See what I'm saying? Both of them are motion energy. So here we have not just kinetic energy 1/2 mv squared for this case, we also have rotational kinetic energy. Okay? So as the wheel or the ball is going around, it's actually spinning like that. And by the time it comes down here, if I'm asking what is the velocity v, well, it's not going to be the same as this v. Why? Because part of that energy, mgh, has been taken up by the rotational part. So what we do in this case, we say that the total energy is kinetic plus u. This is what we have been writing, but I'm going to add something else to it. So I'm going to add the following. Translational kinetic energy plus rotational kinetic energy plus the potential energy u. This one. See that? This is very important when it comes to rotation. When it's rotating, here it has two motions at the same time. The first motion, the wheel is spinning, and the second one, the wheel is moving forward. It's like your car. You know, when you're driving your car is not really going forward exactly. It's actually it causes the wheel to spin. As a result of that, the car moves forward. So it has two motion: spinning wheels and the car moving forward. Two motion. One is translational kinetic energy, and the other one is a rotational kinetic energy of the wheels. You got it? Now, for this case, the translational kinetic energy is what you know, 1/2 mv squared. And for the rotational is 1/2 I omega squared. Of course, the U is mgh. 1/2 I omega squared. Omega here is how fast it's spinning, angular velocity. And I here is what we refer to as the moment of inertia. Okay, the moment of inertia. Moment of inertia is, what is the moment of inertia? Moment of inertia is the resistance of the body to rotation. Resistance of a body to, or let's say rather, to change in rotation, or to rotation. Let's just keep it simple. Okay? And this moment of inertia, I, by itself, usually it's equal to a number, mr squared. Generally, not all of them. I would say 90% of them, they're equal like that. You have a number, and then the mass of that rotating body, say the wheel right here, and the radius of the wheel, radius of the ball, whatever, but with a number. To explain, I can look up a table for you. It's on page, let me go to page 300 here. I thought the table is here, page 300. Should have the same book. Rotational energy. Maybe next page. Sorry about that. Oh, there it is, right here, right there. Up, right there. It is 300. There it is, right here. These are the one. Oh, I didn't go further down, you know, but there they are. So this is the table of moments of inertia. What is the table title? Okay, moment of inertia from any solid objects are tabulated and found online. You would need, and so on. So anyway, so for example, let me just give you some of them. Here you have for a thin rod, you know, any stick, for example, and it's spinning about the middle. It's equal to, like I said, remember I told you it is number mr squared. R is the radius of rotation, and there is a number. Usually that number is a fraction, half, 3/2, and so on, or maybe 1. But it's just usually a fraction. So for the case of the rod, spinning about its center is 1/12 ml squared, L being the length of the rod. If it's spinning on its side, 1/3 ml squared. Okay, and then you have a slab and a slab on the side. Again, maybe this is not important, but anyway. So we have here a cylinder or a disc or a wheel. So that's 1/2 mr squared, R being the radius. For a hoop or a ring, it's mr squared without the half. So there is a 1 here, if you know what I mean. The number, that is. And then we have a solid sphere, a ball, it's 2/5 mr squared. And then for a spherical shell, okay, 2/3 mr squared. Now, if you look at all of them, which one has, and we said that look at the definition. Moment of inertia, the moment of inertia is the amount of resistance of a body to rotation. Okay, how much does it resist rotation? Which one is the least to resist rotation. And if you look at it, you will find that the sphere, okay? In other words, the sphere, the ball, is the easiest to spin, say, than, say, a ring or a hoop like that, and so on, okay? Okay. Let me show you an example from the book on how to apply all these ideas. Go to example 12.4. Says the speed of a rotating rod. So what you have, basically, you have a rod right here. It's held on at one side, say to the wall, and then it's allowed, you let go, and it's allowed to rotate until it hit the wall here. So it says a 1 meter long 200-gram rod is hinged at one end, which is right here, and connected to the wall. Connected to a wall. It is held out horizontally, then released. What is the speed of the tip of the rod, which is at the bottom right here, as it hits the wall? So here is the picture magnified. So here's the rod. The center of mass is right in the middle. The length of the rod is 1 meter. We are holding it here, let's say between my fingers right here, and then I'll let go. It's going to spin like that. Now notice that as it spins like that until it hit the wall, there is no translational motion. In other words, 1/2 mv squared is not there. Remember, 1/2 mv squared, it moves from one spot to another, to another, to another. Here, it is held in its place and it's just spinning, remember? So the side here is not really moving at all. You get that? So it's just spinning. So the nature of the kinetic energy here is all rotational. Got it? 1/2 I omega squared. Okay. Okay, so let's see how we do this. I'll move it to the side here. So let me make a drawing of it. So what I have in here, here is the rod horizontally first. Something like that. This is the hinge right here. And then I let go. And here is the rod later on. If I can do it right there, not the best, but you get the idea. I think a little longer. Right here. Okay, and the center of mass of the rod is right there. So what's happening is that the center of mass is spinning, so it's making a quarter of a circle, if you know what I mean. I can't do this. I'm not doing it well. Whoop. Something like that. There's the center of mass right here. And this tip is also going in a semicircle, bigger circle. Something like that. And then there is the velocity of the rod like there. This is V, okay? Right before it hit the wall, if you know what I mean. This is the velocity of the center of mass. And the length of the rod is 1 meter. You know what? Let me call it L, and that's equal to 1 meter. Like that, okay? Of course, that's also L. Like that, okay? So, what's given to us? It said the mass of the rod is 200 gram, which is 0.2 kilogram. The initial velocity of the rod is 0. Find the velocity at bottom. Okay? Again, let me repeat again. Since the side of the rod is held in one place in the hinge, it's fixed, okay? That means there is no translational kinetic energy, okay? 1/2 mv squared does not exist. But we have rotational kinetic energy, 1/2 I omega squared, okay? So if I'm going to pick two places for conservation of energy, one when right before I release the rod right here, and then here right before the rod hit the wall, okay? The two energies here are equal because of the conservation law. So one way to think about it is, let's see, how do I do it? I'm talking about the space. I'm trying to find a space where you can also see the screen while I... so if we look at, if we follow one way to do it, let me follow the center of mass, okay? So the center of mass is right here. So what's going on in the center of mass in terms of conservation of energy? So look at the center of mass. So before release, what was the energy available to the center of mass? And the answer is all potential, right? It's just the height of from here. I mean, we are assuming that the height of the rod is somewhere here. Here where U0, the potential, which means the height is 0 here. See what I'm saying? So it basically, the height of the center of mass is basically L, the length of the rod, before release. And that's the only energy available to it, which is basically mgl. Again, I'm following only the center of mass. Now, here, right before it hit the wall, right there, again, I'm only following the center of mass. What would it be? Well, it went down like that. So there has been a loss of potential to rotational kinetic. Rotational kinetic means 1/2 I omega squared. I don't know omega yet, but that's basically what it is. But when the rod is here, the potential is not 0. The potential at the center of mass is not 0 because you still have this height. See what I'm saying? So this height from the 0 potential here is equal to mgl over 2. I hope this is clear. There we go. That's basically the equation or the conservation of energy for the center of mass. So this is before release right here, and this is after, or just before it hit the wall. Okay? Now with this information in mind, I can solve, do I have everything? Well, maybe. Let's see. I can move this to the other side. So I have here mgl minus mgl over 2 equals 1/2 I omega squared. Okay? So that will give me mgl over 2, right? And 1/2 I omega squared. Why am I doing all that? Well, I can solve for omega. What is I here? Well, that's I for the rod. Let me go back to the table. Right here. And it says the rod, I have this one spinning about its center. This one's spinning about its side. Which one should I use for the I, for the moment of inertia? Obviously this one, because the rod here, our picture, it shows that the rod is spinning about its side. Like this one, oops, the rod here is spinning about its side, which is 1/3 ml squared. Okay, so that's the value of R that we're going to be using. So go back to this. So that's going to be mgl over 2 equals to 1/2 1/3 ml squared times omega squared. Okay, so I can do some algebra now. Half cancel out. The L here and the one of the L's here cancel out, and I keep working on it. I will end up with omega equals to mgl over mgl over what? Mgl. Let me do it again. Sorry. So that's I'm looking at my notes and I'm doing it in a different way. So anyway, I have here mg. Let's do it slowly. So I have mg equals to 1/3 ml omega squared, and the m's cancel out. I forgot to cancel the m's. So therefore, omega is equal to 3g over L under the square root. Is that okay? There we go. And now we calculate that. So that's going to be 3 times 9.8 times L is 1. All of that under the root. And then we calculate that. And that will give me 5.4 radians per second. Okay, so what I've done here, I use the motion of the center of mass to find omega. Now he's asking me, go back to the problem, he's asking me what is the velocity at the tip of the rod right here. Okay, it's not going to be the same as velocity of the center of mass. It's actually going to be faster because it has a larger radius. You see what I'm saying? But that shouldn't be a big deal because I know that the velocity in general is equal to omega r. I already found omega, and as I told you in the previous problem, omega is for all parts of a rotating body, all of them. So here we have, for our case, the r here is basically the length of the rod. So basically I can write it this way. That's equal to omega times L, the entire length of the rod. And that will be equal to, omega is 5.4 times 1. And that's equal to 5.4 meters per second. Okay, now I'm done with the problem. If he tells me, let's say, what about, let's say 3/4 of the way right here? You know, let's suppose that this is 3/4 of L. That's easy. Just, it's the same thing. So V equal omega r, and then r becomes 3/4 of L, and so on. Okay, whatever length, whatever radius you give me, I can do it. You see what I'm saying? Okay, and that's it. Okay. Okay, the next topic that I want to talk about is a very important topic. It's called the parallel axis theorem. The parallel axis theorem. The parallel axis, I'm trying to make it look better. Parallel. Okay, so this is a very, very useful theorem, especially in the field of engineering. What it says is the following. Suppose I have a cylinder, okay? I'm going to explain it to you through a simple example. Suppose I have a cylinder. Here is a cylinder. And let's suppose that the cylinder is spinning about its axis, its central axis, which is right here. All right, so it is the axis of the cylinder, and it's spinning about its axis like this. Omega. Okay, and all right, so if I ask you the question, what is the moment of inertia of the cylinder as it spins about its axis? Well, you're going to say easy. I can look at the table, and it's going to be 1/2 that it is right here. So you have a cylinder spinning about its axis, or a disc or a wheel. It's equal to 1/2 mr squared right there, right? All right, fair enough. So here I is equal to, whoops, 1/2 mr squared, r being the radius of the cylinder, correct? All right. Now here is a question. What if I want to have the cylinder rotate not about a central axis, but rather off the axis, say somewhere here or somewhere here, like this? Imagine I want to have the cylinder spin about this side right here, about this point, somewhere here. For whatever reason, I am an engineer designing a cylinder that will spin something like that, off center. Something like, when you have your cell phone and you set it to vibration mode. Well, what is a vibration mode? It's basically a cylinder or a disc rotating off center very, very fast, and that will give you that sensation of vibration, I think. It's just off center. Now the question is, what is the moment of inertia of this cylinder, where it's spinning about, off center? Suppose, let's say, if this is the radius r, suppose that this is a radius of, let's say, r over 2. It doesn't look like it, but let's say it's r over 2. Okay, so what is the moment of inertia? Well, here is where the parallel axis theorem, the PAT, comes to the rescue. The parallel axis theorem tells you the moment of inertia for an object rotating off center is equal to the following simple formula. The moment of inertia about the center of mass, which is basically that, this I here. That's the moment of inertia about the center of mass, mr squared, or this one, center of mass, plus md squared. That's the formula. I would urge you to memorize it. M here is the mass of the cylinder, just like the mass here. And d, how far is it from the center of mass, which is r/2. Okay? Got it? So in other words, if I want to measure, calculate the moment of inertia of a cylinder rotating off center, all I need to know is how far is it from the center? The axis of rotation, that is. How far the axis of rotation from the center. Once I know, I can calculate that. So for our case here, it's going to be 1/2 mr squared plus m, how far is it from the center? r/2. So r/2 squared, like that. And then I can just do the algebra, 1/2 mr squared plus 1/4 mr squared. So the moment of inertia is 3/4 mr squared. See that? And there we go. I have calculated the moment of inertia of this cylinder. Another example that is cool, to use the parallel axis theorem, it says find MOI, moment of inertia, of a thin rod about an axis through one end. How about that? Okay, through an axis of one end. In other words, let me make a drawing of it. So here's the rod right here. Okay, and I know, suppose that I know that the rotation about the center of mass right here is given to me in the table. I can look it up. Right here, right? And it is 1/12 ml squared. He's saying, what is the moment of inertia at the end here? Well, it's equal to 1/3. Let's say we don't know that, okay? So I want to use the moment of inertia and calculate this one. So he said, if this is I center of mass and it's given to me, it's 1/12 ml squared, L being the length of the rod, m is the mass of the rod. He said, what is the moment of inertia about the side? Oops, about the side right here. I. Well, according to the parallel axis theorem, I is equal to I about the center of mass plus md squared. D is what? How far is the center of mass to the new axis of rotation, which is basically this one. That's D. Okay? And for our case, it's basically L/2. I hope you believe that, right? So that's going to be 1/12 ml squared plus ml/2 squared. If we do this correctly, the answer should be this number right here. Excuse me, this expression right here. Because that's for the moment when I'm on the side. And now you know how they got that, actually. I mean, they knew this one. How did you get this one? Well, parallel axis theorem. This is how you get it. Oh, this one. You know this one is the center. So on the side, well, it's just md squared. You can work it out, and you can get that number. Anyway, so let's do it and see if we get 1/3. So that's 1/12 ml squared plus 1/4 ml squared. And so 1/12 plus, so that will be what? 1/12 plus 3/12 ml squared, and that will give me 4 over 12 ml squared, or 1/3 ml squared. That's exactly what we have, right? And there we go. Got it? Good. Okay. Now we move to the concept of torque. Torque. So what is torque? Torque is the best way to define it. It is the rotational equivalent of force. So think of it like a rotational force. Think of it like it's a force you exert on an object and you cause the object to rotate about a specific axis. Okay? So it is the rotational equivalent of force. If you look up 20 physics books on the definition of torque, you will probably find 20 different definitions. Anyway, so that's one way to define it, at least in our book, the rotational equivalent of force. That is a decent definition, it's fine. Rotational equivalent of force. Okay? What that means is the following. Let me explain it to you in simple terms. Imagine, let's say on the floor, I have, let's say a rod. Okay, let's say it's sitting on the floor right now. Okay, and what I'm going to do, I'm going to kick the rod right in the middle, right here. So what's going to happen to it? Well, it's just going to move in a straight line like that. There it is. Okay, just going to go this way. Okay, because I have exerted a force on it, and right on the center of mass. There's the center of mass. However, if I take the same rod, here's the center of mass, right? But now I'm going to kick it on this side. So what's going to happen to it? Well, what's going to happen is going to spin like this. And then it's going to go like that. You see what I'm saying? And so on. It will just start spinning like that. As maybe it go forward, but let us be spinning like that. And what happens is that I have exerted torque on it. And torque, tau, the Greek letter tau, is equal to R cross F. Or, in simple term, tau is a vector. Tau is equal to R F sine phi, or sine theta. That's the formal definition. I'm going to show you how to apply it. But that's the formal definition of torque, okay? Tau, remember this second form right here for the level of physics that you're taking. RF sine theta. R here being what? Let me go back to this example, right? This one right here. Change a different color just to show you what R is. R here is a radius. Radius of what? Well, the radius or the distance between the center of mass. Oops, did I change the color? I didn't change the color yet. Hold on. Okay, there we go. Basically, let me do it here. Okay, here is the rod right there. Okay, here is the center of mass. Here is my force applied on the rod, not necessarily on the side of the rod. So this is the force, the applied force. The distance between the applied force, the perpendicular distance that is, to the center of mass is the rod, the radius of rotation here. This R. Okay, we call it the moment arm. The moment arm, okay? The word moment means turn. Did you know that? A lot of people don't know that. It means turn. So when I say just a moment, I'll be right back. Just a moment. It's just a turn. A turn of what? Turn of the clock. You know what I mean? Turn of the clock. That's the meaning. So the moment arm, the turn of the arm, okay? So the arm is going to turn here, and that's the turn of the arm, the distance, R, okay? So it's called moment arm, and this is the force applied. Another example to show you what that means, let's say you open up the door of the bathroom, okay? So it is the door. I'm talking about a top view. Here is the hinge. Here is the knob. That looks something like that. And let's say that you want to pull it, so you pull it to open the door. So the door goes like that. So you apply a force F this way. And it's turning around the hinge right here, right? So the distance between the knob, where the force is applied here, is the moment arm, R, okay? And the torque in this case is going to be what? RF. RF, if R and F are perpendicular, like in this case, see, they're perpendicular. You see what I'm saying? If there is an angle between them that is not 90 degrees, it becomes sine theta, sine the angle between them. Get that? I'll show you an example in a second. Okay, good. Here's an example. I think this one from the book, example 12.8. Let me go to it very quickly. 12.8. Page 305. Oh, 305. There it is right here. So interpreting torque. So torque, basically, let's just go over those nice pictures. So you have a cyclist is pedaling his bicycle. So he or she is applying a force. The moment arm is going to be basically the length, this arm right here, the radius, because the center of mass, if you will, is right at the center right here. And then you have the force applied. Let's suppose it is in perpendicular motion like that, or whatever it is, maybe like this. And then this angle between them is the angle, phi, okay, and so on. Or you have a wrench and you're trying to, turn the knot. So let's say you pull this way. So the distance from the point of application right here to the pivot point is the moment arm, okay? And its tau is equal to RF. The F here again, the F is a force, but you don't put sine theta if R and F are perpendicular, okay? So with this example, however, is that the one? Yeah, right here. So what you have in here, you have a wrench. Here is the knot. The distance from the center of the knot to the point of application, this is where your arm is, let's say, your hand holding it, is 20 centimeters. The angle here is 30 degrees, okay? And the force is this way. Of course, you want the force that is perpendicular to it, okay? So you can use either this force sine the angle, or you just take the component of that force. Let me read the problem for you. So here it says, Luis uses a 20 centimeter long wrench to turn a knot. The wrench handle is tilted 30 degrees above the horizontal, and Lewis pulls straight down. So he pulls straight down. This is the red vector right here, not this one. The red vector here. Straight down on the end with a force of 100 Newton. How much torque does Luis exert on the knot? Okay, so I don't like the way he solved it. What you want to do, basically, is that, like I said, the force and the moment arm have to be perpendicular. This is very, very important. They have to be perpendicular. And so since this is the force, so you basically want to get the perpendicular component of this force, which is this one. He's calling it F sub t, t for tangential. Okay, so how you do that, it doesn't really matter. He uses this angle 120 negative. If you're comfortable with the way he did it, that's great. But I'm going to do it my own way. Okay, so how do we do this problem? Let me show you. Okay, so let me draw the wrench. So what we have the wrench. Here it is. I think I can draw a wrench very quickly. Something like that. Here is the knot. And that's all right. Just go like this. Sorry for the lousy drawing. I could draw better than that if I was on using chalk or something. And so let's say that the force of application is right here. He is applying this force right there. This is the force. And of course, like we said, it's a must that the force have to be perpendicular. So this is the one we are interested in. And the radius, of course, is here. Given to us. The number is given to us. Okay, there we go. And so, sorry, not this one. So what I have in here is something like this. This is 30 degrees. And so if I can, what I could do, I can take this triangle right here. Okay, here it is. That's the angle 30. This is R right here. This is the force he's using. But the force that I want is this one. Because this force is perpendicular. See that? It's perpendicular to the moment arm. This is the force that I always want. Okay. Let me go back and write this one down so you want to keep that in mind. Is that let me just put it back here. Here, must. If you're taking notes, probably you want to box it. Must R perpendicular to the force. Okay? It has to be perpendicular to it. So if it's not perpendicular, you want to find that perpendicular. You get that? So how do we do this problem? Well, if this is 30 degrees, this must be 60 degrees right here. Okay? So this is F sub t. So how would I find F sub t if I know that this is the force? So one way to do that is to F sine 60 will give me F sub t. So F in this case, you can pause the video and think about it. So here we have F is given to us. It's equal to, right there, 100. So we have here 100 times sine 60 is 0.866. That will give me F sub t. And that would be equal to, F sub t is equal to, what is it, 86.6 Newton. Now, another way of doing it is he's taking this angle right here, along the line all the way there, and that will be sine that, okay? Sine 120. You should get the same answer, of course. And now, so what is the torque? Well, the torque is RF, so that will be equal to, R is given to us right here, 20 centimeters. F, remember, this is F sub t, so that's going to be 0.2 times 86.6, and that will give me 17.3. And what is the unit of torque? Well, this is meters, this is Newton, so Newton meter. And that's the torque. Now look at the direction. There's one more thing, one more item. Because torque is a vector, so you want to take the sign of the vector. So it's moving this way. So Luis is pushing on it this way. So it's going to go clockwise. See that? It's going to go clockwise, and clockwise is negative, so you just put that minus sign right there. Because it's clockwise. Tau is CW. You see what I'm saying? So that will be one way to do it. Again, or if you want to use this formula right here, tau equals RF sine phi, you can do the same thing. So you can say tau equals RF sine phi. And the phi in this case is going to be the 60 degrees right here. And we can just plug it in. You get the same answer, of course. So that's going to be 0.2. F is 100. sine 60 degrees, and then you'll get the same answer. And pay attention to the sign of it here. You know, is it clockwise or counterclockwise? This is very important. Very, very important. We're going to do some more problems later. Okay. So that's basically how you do it. All right. I'm going to do at least a couple of more problems on torque. Let's see. More than that, really. Maybe I'll do 3-4 of them. Here's another one from the book, an example 11, 12-11. Let me show it to you. These are, I hope they're simple examples. 12-11. It's the fan. Huh? Page 309. Kind of a simple problem. Here it is. So let's read it together. It says an engine, this is an engine, in a small airplane is specified to have a torque of 60 Newton meter. Okay? So you have a 60 Newton meter torque on this engine. Is the axis of rotation. This engine drives a 2 meter long 40 kilogram propeller. Okay, so this is the propeller. On startup, how long does it take the propeller to reach 200 revolution per minute? All right. Okay. So what you have, let me draw the propeller. So you have something like this. It's already lousy, sorry about that. There we go. And there we go. And it's spinning like that. The length of the propeller, it's not vertical, sorry about that. I'll just go like this. It's 2 meters. I'm going to call it L equals 2 meters. And the mass of the propeller is 40 kilograms. And the torque that is causing the propeller to spin, to rotate, is 60 Newton meters, okay? And he says, let me go back to the problem again. The engine is small. So we have a 2 meter long, 40 kilogram propeller. How long does it take the propeller to reach 40 revolutions per minute? Okay, so we are starting with probably omega naught equals 0. Or maybe F naught, the initial frequency is equal 0 as well, right? It's still not spinning and then, right? So, but the final frequency is 200 RPM, and I can convert it, of course, into hertz. That's easy. Let's do it quickly. So 200 rev per 60 second, you see what I'm saying? And then we can get that, and that will be equal to 3.33 hertz. That's the final frequency. I'll come back to it. He said, how long? Let me go back again. How long does it take to reach 200? All right, that looks like a kinematics problem. You know, rotational kinematics. So he's asking for the time. Now, let me get the corresponding omega for this one, which is 2 pi f, right? So that will be equal to 3.33 times 6.28. Oops. One more time. 3.33 times 6.28. Answer 20.9 to be more exact. 20.9 0.9 radians per second. How about that? Okay, so that's omega. Now, how long? Well, I know that I can use rotational kinematics. If you go back to the rotational, here they are. Omega equals omega naught plus alpha t. Omega squared equals omega naught squared plus 2 alpha theta. And then theta equals omega naught t plus 1/2 alpha t squared. The one I'm going to use is the one, the first one, probably the simplest because it's asking for the time. And I don't know alpha yet, but I want to show you how to find it. Okay, so what we have in here is omega equals omega naught plus alpha t. Now, since the propeller is starting from rest, so that means omega naught is 0, right? So that's 0. So I have here omega equals alpha t. I'm almost done with the problem, as you can see. I already know what omega is. I can just plug it in. And he's asking me for t. All I need is to find alpha. Once I find alpha, I'm done with the problem. Well, how do I do that? Well, here's something that I did not mention purposely until we get to this problem. Let me just digress a little bit here. So far we have studied the following. Linear motion, or we said that F equals ma, right? That's for linear motion or translational motion. And then we have rotational here, right? For rotational motion, we said that tau is equal to Rf, okay? Rf here, think of it like a force, the force part. But as a result of this torque, we will have a rotational motion. That rotational motion is equal to I alpha. I here is moment of inertia, and alpha is the angular acceleration. So what is I alpha? It's equivalent to ma. Remember ma? Ma is what is the kinetic reaction of a body as a result of the forces F on it. Okay, so you have a bunch of forces on a body. As a result of that, the mass of that body moves with some acceleration. So the product ma is what we call kinetic reaction. Well, what about if you have a bunch of forces on the body that will cause it to spin, to rotate? Well, as a result of that, it will move in a rotational way, and that rotational kinetic reaction, if you will, is equal to the moment of inertia of that body times the angular acceleration of that body. You get that? This is very, very important to keep that in mind. That's the meaning of it, okay? So we have F equals ma and tau equal Rf, or tau equals I alpha for the kinetic. So this is kinetic reaction. Remember, kinetic reaction means what? Forces F, these are some forces, some of the forces. Forces on a body that will, as a result of that, it will move in some acceleration. Here, forces on a body, sigma tau, if you will, forces on the body, as a result of that, it will rotate, okay? And that rotational kinetic reaction, rotational kinetic reaction is equal to I alpha, okay? So what he did in this problem, he gives me the torque. He said the torque is 60 Newton meter. So all I need to do is to equate it to I alpha. I, the moment of inertia of this, the propeller. I'll come back to it in a sec. So let me do that. So I have here, but tau is equal to I alpha. And I is given to me. It's equal to 60 right there, guys. Okay? What is I? I is the moment of inertia of the propeller. Well, look at the propeller. It approximates a rod spinning about its center. You see what I'm saying? That's, I mean, it's not exactly accurate. I mean, if you are actually working in as an engineer in this company, you're not going to use the rod. You're going to probably calculate it very, very accurately. But for the time being, we're just going to say it's approximately, it rotates, it approximates a rod spinning about its center, which is, if you remember, go back to the table, 1/12 ml squared, L being the length of the rod, 2 meters, okay? And now plug it back in here. So that's going to give me 60 equals to 1/12 ml squared times alpha. As you can see, I have everything, and I can easily find alpha now. So alpha is equal to 60 times 12 divided by m times L squared. Then I'll plug in my numbers. Remember, guys, keep this in mind. This is the one that we are being asked to find, the T here. And then we just plug in our data. So we have here 60 times 12 divided by the mass. The mass of the propeller is 40 kilograms times L is 2 squared. And then when I calculate all that, I end up with 4.5 radian per second squared. There it is. So now I go back to my formula right here. So therefore, T is equal to omega over alpha. Omega, I just got it right there, right here, 20.9. And alpha, I just got it. So 20.9 divided by 4.5. And that will be, when we do that, I will end up with 4.65 seconds. So it will take the propeller 4.65 seconds to reach an RPM of 200 RPM. See what I'm saying? I like this problem. Kind of a good review of things that you've studied in the past. Okay, one more. I have at least 2 or 3 more. Oh, we still have angular momentum to cover. Okay. Okay, let me go to problem number 59 in the textbook. Okay, let's look at number 59 right here. So what you're looking at, you have a beam, you have a worker resting, you have a cable hooked up to the wall, and then at one end of the beam, and the beam is attached to the wall in that fashion. This is 30-degree angle, and the length of the beam is 6 meters. All right. So let's read the problem. He says, an 80-kilogram construction worker sits down 2 meters from the end of a 1,450-kilogram steel beam to eat his lunch. All right. What's the tension in the cable right there? Okay. What's the tension in the cable? There are several ways to do it, but we're going to do it in the method that we are studying right now, and that is the torque equation. So first thing you need to do you want to make the free body diagram. But I'll tell you what, before I do this problem, I want to give you a simple example. And you need to pay attention to this example because it is extremely important. It will help you solve this type of problem, which you will see later on when you take a course, advanced course in statics and dynamics and engineering. You're going to see those kind of problem, but more advanced problem. So pay attention to this example that I'm going to give you. I want to do it before I do this problem. Imagine you have a window cleaner, okay? A person, let's call him Joe. A window cleaner, he's standing on a scaffold, and he's hung from say 2 cables. And so let me make a drawing. So what you have a beam or a scaffold. It's not very good. Here it is. Sorry. There we go. And let's say our friend Joe is, let's say, situated right here. There he is. and he's cleaning the window. He's this rag, if you will. And let's suppose that there is a bucket right here. This is the bucket he's using to clean the window, okay? And then there is a cable here and another cable here. Just take it really simple, okay? I'm going to call this the cable here, cable number 1. It gives you tension number 1, and this is tension number 2, okay? Suppose the length of the beam or the scaffold is 10 meters. And let's say the bucket is at the distance of, let's say, 4 meters from this side, okay? And then Joe, let's make him 3 meters from this side, okay? Also, suppose that the mass of the scaffold, I'm going to call it M sub s, let's say, just pick a number, let's say 100 kilogram. The mass of Joe, let's make him 80 kilogram. Let's say the mass of the bucket, M sub b, let's make it 20 kilogram. The question now, find the tensions in the cable, T1 and T2. That's the question. All right, how do we do something like that? Okay. Well, if I'm going to apply the Newton's laws, the one we studied back in chapter 6, 7, and 8, so we can say that I can convert this whole thing into a free body diagram. Here is the scaffold again, and I have tension T2, tension T1. Remember, tension always comes out of the body, and this is the force from, let's just call it the weight of Joe, right? So that's mg Joe, mjg, if you will. And then we have the weight of the bucket, m sub bg. And don't forget the center of mass of the beam, which has a mass. Remember, it is right here, the scaffold. So it is m sub s g. You see what I'm saying? So now I can say the sum of the forces is equal to 0 because the whole thing is in equilibrium. It's not moving. So I can easily collect all these forces. It's going to be T1 plus T2 minus mjg minus msg minus m sub bg equals 0. Let me just continue on with it. T1 plus T2 minus, what is it, ATG for Joe minus 100G, G here for 9.8, okay? I'm trying to just do it in one shot, for the scaffold minus the bucket 20G, if you will, right? Equals 0. Or I can say T1 plus T2 plus, let's actually minus, what is it, 200 times 9.8 equals 0. And when I calculate that, 200, that gives me 1,000. So basically what I'm end up with, T1 plus T2 equals 1,960 Newton. And there it is. This is the combined tension, okay? But he's asking me what is T1 and T2. I don't know. I know the total is 1,960, but I don't know how much is T2 and how much is T1. I don't know which one is larger than the other. They're not necessarily equal, okay, because the system here is not symmetric. You see what I'm saying? It's not symmetric, so they're not necessarily equal. So as you can see here, there is a problem with the F equals ma, or F equals 0, sum of the forces, is that it doesn't give me always the answer that I need. So that's why I have to appeal to the torque equation, tau, to solve this problem. You understand? So how do we do it? Here's how you do it. What we have done so far is not a waste of time. We're going to use all these formulas that we have done later on to solve this problem. So what you do is the following. Remember, torque is all about rotation, okay? So what you want to do, go back to this is a picture that we have. Joe is cleaning the window, you get the bucket and all that, and you have those distances. Notice that Newtonian law, sigma f equals 0, we did not bother with those distances. Moment arms, if you will. We did not bother with it. Here's how you do it. When you use torque, the first thing you want to do is you pick a point, okay? You pick a point and then you take the torque about it, okay? I'm going to pick this point right here. I mean, it doesn't really matter which point, but I'm going to pick the point right here. I'm going to call it point A. Call it whatever you like, okay? So what I'm going to do, or right here, this point, same point, right? So I'm going to take the torque, if I can spell it, about A. What that means, sigma tau about A equals 0. Of course, the whole scaffold system is not rotating. Let's hope Joe is not going to rotate. That'll be a problem, right? So it's in an equilibrium. Just like sigma f equals 0, another statement for equilibrium, sigma tau equals 0. Okay? You got it so far? Okay. So what you want to do now, let me go back to this one here. Let me change the color so you can see it. Pay attention. This is interesting. So I'm taking the torque about this point right here, right? So think of it this way. Here is this force right here. Think of that. Imagine that this force is going around this point, or going around it in this direction, clockwise. This one is going around this point also, in the clockwise direction. Think of this one is going around that point, okay, in the clockwise direction. And this one, however, T2 that is going around this way, okay, in the counterclockwise direction. So the torque is what? Tau is equal to RF. So if I start with MJG right here, well, this is R right here, and F is basically MJG. Okay? Clockwise is negative, counterclockwise positive, and they're going to add them up together. Do you see the plan? Let's do it. So the way we're going to do it is this. Sum of the torques, I'll just give it in red, about point A is equal to the following. Let's start with MJG right here. Well, MJG is ATG, or whatever it is. MJG times how far is it from here? Well, according to this, 3 meters. See that? So that's going to be MD, and it is clockwise. That's going to be a minus. So minus MJG times 3. Got it so far? Okay. Now this one also is going to go this way. That's clockwise. How far is it? 5. Remember, the length of the scaffold is 10. Center of mass is always at the center, so that's 5. So that's going to be minus MSG times 5. Okay? Now we're going to do it with the bucket. The bucket is here. Remember, we are taking the torque about A, not this one. So that's going to go like that. Clockwise, negative. How far is it from there? Well, look. We are given, this is 4. This must be 6 then. So that's going to be minus M bucket G times 6. And then the last one is this vector, T2, going this way. That's positive because it's a counterclockwise. How far is it? 10 meters. So that's going to be plus T2 times 10. Enclose everything. There we go. And guess what? I can find T2 with this equation. Do you see that? I mean, everything else I know. So that's going to be minus 80 times 3. I'm going to take the G as a common factor, so bear with me. Minus M sub S, which is the scaffold, 100. So that's going to be 100 times 5 minus B is the bucket, is, I forgot what it is, 20. So 20 times 6, all of that times G plus 10T2 equals 0. Let's do that very quickly. So that's going to give me, so I have here negative 240 minus 500 minus 120, correct, times 9.8 plus 10T2 equals 0. As you can see, I have nailed it. I was able to solve it. And multiply. I'm using my calculator because I made up all these numbers. So I have here 8,428 plus 10T2 equals 0. Oops, with a minus sign here. And then, so therefore, T2 is equal to 842.8 Newton. There we go. I know what T2 is. Now I can appeal. I'm done with basically this part of the problem. I can appeal to the Newtonian formula, sigma F equals 0, right here. And I got that the sum of T1 and T2 is 1,160. I can take that, I can appeal to it, plug in T2 in there, and then solve for T1. I can do that. So therefore, T1, which is equal to 1,960 minus 842.8 842.8 minus 1,960. Answer, if I did it correctly, I hope I did, and that's equal to 1117.2 Newton. And there we go. I have the two forces. You got it? Okay. This is a very important problem. I hope I would urge you to stop the video and try to do this problem by yourself without looking at the solution here. Okay. All right. So let me go back to the problem that I'm working on. That's number 59, which is very similar to this one, except that we have an angle here for the force, you know. So let me make the drawing first. So that's number 59. So here is the wall, if you will, and here is the steel beam, like that. And that is the cable all the way to the end. And then we have the worker. I'm going to put him as a box like that. And of course there is tension in the cable, and that's what he's asking for. This angle is 30 degrees. I'll call it theta for now. And this is the scaffold, or whatever you want to call it. Something like that. And then this one is 6 meters long. Okay. Okay, so how do we do it? Well, you want to reduce this problem into a free body diagram. So here is the beam. Okay, and I have the tension going this way. Here's the angle theta. I'll come back to this number later, T. And then I have the mass of the beam itself right here. I hope he gave it to us. Did he give it to us? I think he did. Yeah, so we'll call it the mass of the beam, M sub B. And then we have the worker, the mass of the worker right here. I'm going to call it the mg here, sorry. This is the worker, mw maybe? G, like that. What else do we have? Well, we have something going on here at the wall. There is some forces here, I'm sure, right? I mean, imagine if you put your finger between the beam and the wall, it's going to hurt because there is a force here. There is a push here. but I have no idea what it is. But I'm going to guess it's going to look something like that. Some force R, God knows what it is, at some angle phi. And it's really not important how you guess it. The reason is because you want to take the torque about that force right here. Okay, and once you take it there, you eliminate it. Okay, so that's basically what we have. Let me put in the dimensions first before I take the torque and solve the problem. So the length of the beam, the full length is 6 meters. And the length to the center of mass, that'll be 3 meters. And then the length to the worker, which is right here, is, he said it's, the worker sits 2 meters from the end of the beam. So that makes it 4, right? And we know, let's see, what else do we have? We have the mass of the worker is 80 kilogram, and the mass of the beam is 1,450 kilogram, right? Okay, so let's take the torque about A. So that's going to be sigma tau about A is equal to 0. Okay, so once you do that, because this force, this ambiguous force R, is right at A, that means the moment arm is 0, so we can ignore it. So the forces that we're going to be contributing is this one, and this one. Remember, this one has an angle, so that's going to be T sine. Remember the sine thing? So it's going to be T sine theta, because we're only going to take the perpendicular component, which is T sine, okay? So now I'm going to build it up, so that's going to be starting, and remember, clockwise, everything is going to rotate about this point. So this is going to go like this. Let me put it in red. We're going to do the same thing. So that's going to go like this. See what I'm saying? Clockwise, negative. This one also negative. And this is going to be T sine theta like that. And that's going to go like that. And that's going to be positive because it's a counterclockwise. You get that? So that's the plan. Let's do it. So starting with MBG, so that's equal to minus MBG. Watch those minus signs. Again, because it's a clockwise. MBG times, how far is it? It's 3. Minus MWG with a minus. How far is it? 4. And minus, plus, plus, that is, T sine theta, or phi, whatever. And how far is it? 6. Equal to 0. There we go. Okay? And I have everything here, as you can see. So, I'll end up with, if I plug in all that numbers, it's going to be minus 3 times 1,450 minus 4 times 80 bracket I have times 9.8 plus 6t sine 30 degrees, and that's equals 0. And then all you need to do now is you do the algebra, the simple algebra, to solve for t. And when you work it out, you're going to end up with 15,300 Newton. That's the answer I got for this. Okay? I hope this is clear for you. I have 2 more problems to work on. The first one is the ladder problem. It's example 1215. It's right here in the book. As you can see here, let me show you the picture. So you have a ladder leaning against the wall, and of course it is positioned on the floor. And then the ladder is symmetric, geometrically symmetric, which means that the weight would be right in the center. We are assuming that. The length of the ladder is 3 meters, and it's touching the wall and the floor at those points right here, and it's leaning with an angle of 60 degrees. Okay, that's just the information from the picture. Let's go back to the problem. It says here a 3 meter long ladder leans against a frictionless wall at an angle of 60 degrees right there. What's the minimum value of mu, which is the coefficient of friction, with the ground that would prevent the ladder from slipping? Okay, so what is the minimum value of mu sub s, the coefficient of static friction with the ground that prevents the ladder from slipping? Okay, so that's basically what the problem is asking. Notice that the mass of the ladder is not given to us. That's not a big deal, because usually when the mass is not given, from my experience, that means the mass somehow will cancel out. Somehow. Okay? Anyway, so let's see how we can do this problem. Let me draw it first very quickly. So I have, here's the wall, here's the floor, and then there's the ladder right here. Okay, and this is the angle. I'm going to call it theta for now. Now we ask the question, what are the forces on it? Well, since it is, you know, the most obvious one, of course, the weight. So there's going to be mg right here. And then it said to prevent it from slipping, so there should be a friction force like that. And since the ladder is touching a surface, the wall surface right here, and the floor surface right here, so whenever an object touches a surface or presses on the surface, there will always be a normal force, one this way and one this way, perpendicular to the surface. That's why we call it normal. We're going to call that N2 because our book calls it N2, and then this one we're going to call it N1. All right, so these are the forces that we have. All right, so what are the equations of equilibrium? Sum of the forces in the x direction equals 0, and sum of the forces in the y direction equals 0. So sum of the forces in the x direction, that will give us what? N2 minus F equals 0. So therefore N2 equals F. I'm going to box this equation. Both N2 and F are unknown to me. All right, so they're both unknown. I'm going to box them. I'll come back to them later. And then sum of the forces in the y direction is also equal 0. So that will give me what? It will give me mg, sorry, minus mg, right? Let me say this, n1 minus mg, how about that? And that will give me n1 equals to mg. Box it again. Both of them are also, both mg and n1 are unknown to me as well. Okay, so far? Of course, if I don't know anything about torque, I'm going to be stuck with those two equations, and I have no idea how to solve this problem. Okay, so I appeal to the torque equation to solve this problem. Before I do that, let me just give you a quick review of what we have done so far. If I have a beam, such as the beam that you see above, which is a ladder, and let's say I have a bunch of vectors on it, something like that. And let's say at the point here I have maybe 3 vectors or something like that. And I want to take the torque, okay? When you have something like this, of course I'm exaggerating the number of forces here. When you have something like that, always take the torque about a point where there are too many vectors coming out of it. Why is that? Because the moment arm here would be 0, right? Moment arm is how far is the vector from the point? Well, it's on the point, so 0. So with this, I mean, when you do that, you basically, if those 3 are unknown, you don't have to deal with them. You don't have to deal, because they all go to 0 as far as they contribute 0 torques. That's what I'm trying to say. Okay, so we have the same thing here. I have here 2 vectors that I don't know, F and N1. So I can take the torque about this point right here, A, I'm going to call it. Okay, so that's what we're going to do. So please draw this picture before it disappears. And I'm going to be taking the torque, you know, while I'm looking at this picture here, or maybe from the diagram that you will have drawn. So we're going to take the torque. So sum of the tau, sigma tau, about A equals 0. Okay? So we begin here. Of course, we're not going to take the torque, or rather, N1 and F are not contribute any torque to this point because they are on the point. So we will have the mg and the N2. However, we have a problem. What is the problem here? Well, if you go back to this one, this diagram, all those forces and the previous problem that we have done are perpendicular to the moment arm, which is the length of the ladder. Here, on the other hand, they're not perpendicular. Okay, so you see there's an angle here. It's not 90 degrees like that. So we have to take the perpendicular component to those. Okay, so what are the perpendicular components? Well, let's see. Let me write it, change the color so you can see it. If you look at this one right here, this is the perpendicular component, which is equal to what? mg, well, sine or cosine? Well, let's see. If this is theta, which is 60 degrees, right? The theta here is 60 degrees. And I have this triangle right here. So this must be 30 degrees, right? This one here. Okay. And this makes it 60 then. Okay. Now come back here. This must be what? I mean, the perpendicular component is going to be this way. See what I'm saying? Let me eliminate this thing. And that's going to be if this is 60 right here, then this also 60. Make sense? This also 60 degrees. That makes it 30 degrees here. So in this case, N2 cosine 30, or we can say that N2 sine 60. Both are correct. I hope you understand all of that. I mean, if you don't, you need to train yourself how to get x and y component of a vector. You know, so maybe you want to pause the video and see why I have done it this way. Okay, so now going back to mg, so what would mg be here? Well, it's going to be either mg, remember mg is going to be either cosine 60, or if you want, mg sine 30, okay? Either or will give you that one, okay? Please try to convince yourself that those vectors are valid. Okay, there we go. So we have that. Now I'm ready to take the torque with this in mind. So remember, N2, we're going to take the cosine for this one, and we're going to take the cosine for this one. Why? Doesn't matter. I mean, either you can take sine and get the same answer. Doesn't matter. So anyway, so what we're going to do? So what we have in this case, plus. Remember, clockwise negative, counterclockwise is positive. So plus mg cosine 60 times L over 2, the moment arm. Remember, the moment arm is what? The length of the distance between A and the center of mass, which is, remember, the whole length is L, it's right there. So that's L over 2. Minus, remember, the mg cosine is this way. That's going to go around it this way. That's that's counterclockwise. That makes it positive. However, the N2 is going to go this way, correct? And that's clockwise, makes it negative. Okay, so we have here minus N2 cosine 30 times L equals 0. Close it. There we go. And now we work on, getting the value of N2. Why do I want to get N2? Because it's going to give me F. And from F, I know F is equal to what? Mu N or mu mg. So in this case, I'm going to get to mu, and I'm done with the problem. You see the plan? So N2 will give me F. Keep that in mind. So I'm going to solve for N2, which is right here. And that will give me N2 equals to mg cosine 60 times L over 2 times cosine 30 times L. If you do the algebra, this is what you'll get. L's cancel out, and then when you work it out, you'll end up with N2 equals to mg over 2 square root of 3. I'm going to box it. How did I get that? Well, we'll get cosine 60. Cosine 60 is half, and cosine 30 is square root of 3 over 2. Work it out, you'll end up getting that. Okay? And then we can say that but F is equal to N2. So that means the friction is also equal to mg over 2 square root of 3. But also, F is equal to mu mg, remember? And so we can equate them together. And so we have here mg over 2 square root of 3 equals mu mg. Of course, we're solving for this mg, the mu. So the mg's cancel out. As you can see, the mass is not important. And then finally, we have the friction, the coefficient of friction, mu, is equal to 1 over 2 square root of 3, or it's equal to, if you work it out, 0.29. So that's mu right here. So that's the minimum value of friction that will prevent it from slipping. Okay? All right, good. Next problem. The next problem is a pulley problem, something that we have done in the past. And if you remember, we always ignored, the moment of inertia of the pulley. We kind of didn't consider it at all. You know, remember the Atwood machine that we have done and some other pulleys? And we didn't take into consideration the moment of inertia of the pulley, whether it's a wheel or a cylinder or whatever. So in this problem, we're going to take into consideration the moment of inertia. And this example comes from my notes. Okay, so what I have in here, let me get this out. So what you have in here, imagine you have this is the edge of a table, okay, and then you have, here's the pulley right here. I'll make it big. I don't need this. Hold on. I'm just having trouble drawing a... Sorry about that. Here is the pulley right here. Okay. And hanging from the pulley or the wheel, we have a small mass here. I'm going to call it small m. The pulley's mass is big M of radius r. Okay? And the pulley is spinning this way as the mass is moving down. Okay? Make sense? Okay, so we have here a wheel, I'm looking at my notes now, or a disc, or what I call a pulley, of radius r and mass big M. All right? He wants to know what is the tension in the cable. Find tension in the cable. And then part B, there are several parts. We're just going to do for the first two. And part B says find alpha, the angular velocity of the wheel, the pulley, and the acceleration of the descending mass. Okay? So that's basically the problem. So the first thing I want to do is, if you remember when we were doing pulley problems, is you take the system apart. So here is the descending mass, M, And what I'm going to do, I'm going to put all the forces on it. So we have a tension here. This is the one we are seeking. And then you have the weight of the descending mass, mg. And of course, it's moving this way, ma, with a minus, right? It's moving down here. Is that right? So in this case, the equation of motion, in this case, it would be something like T minus mg equals minus ma, and therefore the tension is equal to minus ma plus mg. That's not going to help us much. I mean, basically he's asking me for the tension. Well, here is the tension, but I don't know A yet, and he's also asking me for A, remember that. But that's an equation. That's a good equation. All right. Now, the second equation that we're going to do, or take, remember we said we're going to take the system apart. So the other one is basically the pulley. So here is the pulley. So I've taken the mass apart right here. Now I'm going to draw the pulley by itself. Here it is. And I'm going to ask the question, what are the forces on it? Do it again. This is the radius r. And this would be what? That would be the tension. Remember, tension is always coming out of the body. And let me just go back to that picture. Oh, I already drew it. Okay. All right, so what do we have here? What I'm going to do now, I'm going to take the torque about O. Here's O right here. Okay? Now pay attention to how I do it. Remember, torque tau is what? RF. Well, we have R, which is the big R right here, and this is F right here, the tension. Both perpendicular. I don't need to deal with angles here. So basically, and then as it is going this way, remember the direction of the pulley is this way, and that's what? Counterclockwise. That makes it positive. So in this case, the torque, sigma tau, about O, is equal to RT. Or maybe I should say, hold on, I should say plus RT. Is that okay? Now, are we done with that? Well, not yet, because see, remember, we said here, go back to the mass, the descending mass. Where did I get this equation from? This equation right here. Well, I got it from sum of the forces equals ma, or rather minus ma, right? And from there, I got this. Is that okay? Make sure you understand that. Well, I have the same thing. So here we have sum of the torques. I'm a little bit ahead of myself. Sorry about that. Sum of the torques is equal to what? I alpha. Remember we talked about that? I alpha is the kinetic reaction, the rotational kinetic reaction, I alpha. So what does that mean? It means this RT right here is equal to I alpha, just like this collection of forces is equal to MA. So I have here RT equals I alpha. Okay? Now, what is I? I is the moment of inertia. For what? For the disk, or for the wheel, or for the pulley. What is it equal to? Go back to the table, and it's equal to 1/2 big M R squared. It's from the table. Remember, moment of inertia for the disk, or wheel, or pulley. Okay? Put it back in here and solve for T, and the plan is to equate this with that. Watch. So keep paying attention to this. I'll come back to it in a minute. So I'm going to take this and plug it in there. So I'm going to have here RT, big R, big T, equals to 1/2 M R squared alpha, like that. Now equate it with, let me call this equation 1 here. So plug 1. Before I do that, I forgot this R and this R squared cancel out. So I end up with 1, which is minus MA plus MG equals to 1/2 big M big R alpha. Is that okay? Let me solve. Remember, the problem says find the tension T and find the alpha and A. So let me find alpha first, just because I can see it in my head and see it in front of me right here. So what is A here? A is equal to alpha R, correct? Alpha R. So I can take that and plug it in here, and then I have alpha R here, and I can solve for alpha. Do the math, and do the algebra and solve for alpha. That's the plan. So I have here minus M alpha R plus mg equals 1/2 big M big R alpha. Collect the alphas together, which means I'm going to take this and put it to the other side. So that will be mg equals to 1/2 big M big R alpha plus small m alpha R, and take alpha as a common factor. So I'm going to end up with this 1/2 big M big R plus small m big R alpha mg, and then I'm going to solve for alpha, and that will give me mg. And by the way, there are some data that I forgot to give you. Anyway, so we have here 1/2 big M big R plus small m big R. But, okay, given, let me just write it down this way. Given, it's in my notes, so big M is equal to 2.5 kilogram. Small m is given to us 0.51 kilogram. And the radius of the pulley is 0.2 meters. All right, there we go. This is given to us. So I have all of that. So I can just plug him right in there. So plug, and I'm going to end up, I'm going to give you the final answer that I've gotten is 14.3 radians per second squared. There we go. I have alpha. Got it? Now, I have alpha, but A is equal to alpha R, so I can easily find the acceleration, the linear acceleration of the falling mass, if you will. And that'll be 14.3 times R, which is right here, 0.2. And that will give me, therefore, A is equal to 2.86 rather, m meter per second squared. And there we go. I have the acceleration. Finally, now I need to find the tension. I can use the equation number 1, which is right here, guys. I already have A. I got the masses. I got everything. So I just use it. So, and tension, use 1 to find T. So I have the tension is equal to, what is it? Minus MA plus MG. Minus MA plus MG. Or if you will, I can go like this, MG minus A. So let's do that. So the M here is equal to, M is equal to 0.51 times 9.8 minus 2.86. And let me do that. I don't think I have it in my notes here. We have 9.8 minus 2.86 times 0.51. Answer 3.54 roughly Newton. And there we go. Now, another way of getting this tension, by the way, I just thought about it, is this one right here. So remember that? Go back to this formula right here. When we equate the, remember when we, there it is right here. And when we put I in here, we ended up with that. Let me go back to this. This gives me tension is equal to 1/2 mR alpha. I can use that as well if I want to. Plug it in and see if you get the same answer. You should get the same answer. Okay? That'll be another way of doing it for the tension. Okay? I hope this is clear. Okay. The last thing I want to talk about for this video lecture, which is almost getting for 2 hours, is the angular momentum. All right. It's a short subject, but it's very important that you know about it. Angular momentum. So let me talk about that. That's the last topic. Angular momentum. Remember we said, what is torque? We said that torque is the rotational version of the force, right? Rotational version of force. Well, angular momentum, by the way, the symbol of angular momentum is capital letter L, and it's a vector, okay? When I'm writing, I like to write it this way, angle, M, T, M, okay? I think it's a cool symbol when I'm writing, just kind of a shorthand notation for it. So, what is angular momentum? Okay, torque is the rotational version of force. Angular momentum is the rotational version of momentum. We talked version of momentum, MTM. Okay, we talked about momentum. If you remember, momentum is the product of the mass times the velocity, right? And it gives you that collisional power of an object. You know what I mean? Angular momentum is similar to that, and the formal definition of angular momentum in a vector way is R cross P. P here being the momentum, this momentum P here. Okay, that's the formal definition of it. Go back to your book and look at it. Just like, remember, torque, the vector version of it is R cross F. Okay, so that's the same thing. There is a scalar version to momentum, which is the one that you should really know, and it's an easy one. Angular momentum is, angular momentum is R cross P. Remember, P is what? mv, so I can write it this way, R cross mv, like that. So it's basically angular momentum, the scalar version, is mvr, or rmv, without the vectors, and that's true. So it's mvr. This is the one that you should know very well, okay? And it's, it's not more practical. You just see more problems, you deal with more problems that require this version rather than this version, MVR, okay? So that's the mass, velocity, and radius of rotation. What is angular momentum? Let me just give you a simple example, and I'm sure you've heard that for those of you who've taken physics in high school. You know, the skateboard dancer, when she is extending her arm, she's spinning around, but when she brings her arm towards her body, she spins much faster, right? That has to do with angular momentum. I'm going to explain it in a second why. Okay. One more thing about angular momentum before I start doing problems or give you more examples on it is that the Newton's second law what does it say? F equals ma. And if you remember, I also told you it can be written as F equals dp dt, where P here is what? It's the momentum, right? So I can write it this way, d dt of mv. And then look at that. If I do the product rule here, so that's going to be v dm dt plus m dv dt, and of course if we assume that the mass is constant, so dm dt is 0, and we end up with m dv dt, but dv dt is what? Is a, the acceleration, so it's ma. And there we go. That's how we know that F equals ma. It's from this derivation, okay? Now we can do something similar to that. The definition, if you consider, look at this. If I take the angular momentum, we said it's equal to r cross f cross p, right? If I would consider the time derivative of it, look what will happen when I do that. Okay, so that means I'm going to take the time derivative of r cross p. I'm just doing some derivation for you, a quick derivation for you. So that's going to be, use the product rule. So that's going to be dr dt cross p plus r cross dp dt. Is that okay? What is dr dt? Well, dr dt is just v cross p plus, now this one is r cross, what is dp dt? Well, dp dt is right there. It's the force. Is that okay? Okay. Next, look at this. What is v cross p? Well, v and p are parallel. Remember the momentum and the velocity. Remember, momentum equals to mv, which means the momentum is parallel to v. So what is that? The cross product between two parallel vectors? That's simple math, 0. In other words, if A is parallel to B, then A cross B is 0. Go back to your calculus book. Okay? So what we have in here is that this part right here must be 0. So in this case, let me just start from here, dl dt. So dl dt is equal to 0, the null vector, plus r cross f. Well, what is r cross f? Look at that. It's, did I write it down? I thought I did. Here it is. R cross f is torque. Aha. So the derivative of the angular momentum, the time derivative, is tau. Isn't that interesting? So let me review. So we said that tau is equal to r cross f as a vector. Also, tau is equal to I alpha. Also, tau is the derivative of the angular momentum, the time derivative. These are very important 3 formulas for the torque. Got it so far? Okay. So what is the meaning of angular momentum? How do we apply all of that? Well, let me show you. Let me give you an example on the Earth around the Sun. And I'm going to give you this example without any numbers. The way the Earth goes around the Sun is an elliptical way, okay? And I'm going to exaggerate the way it looks. So it is the elliptical. Here's the elliptical path of the Earth around the Sun. Here is the Earth. And where this is called Kepler's first law. We're going to cover that when we cover gravitation, probably next lecture. Kepler's first law says the Earth goes around the Sun in an elliptical path, just like the one you're seeing in front of you, in such a way that the Sun is located at one of the foci of the ellipse. It's not located at the center of the ellipse. You may think the Sun is located here. That's not true. It's not here. It's actually at one of the foci. It's right here somewhere. So this is the Sun, and the Earth is here, going around it like that. Okay? And the way it does, the Earth, it goes here, follow my mouse or the cursor. So it goes here at the low speed, but as it gets closer and closer to the Earth, to the Sun, it goes faster and faster and faster. So it goes faster, 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 fastest here, because that's the closest approach. Okay? And then it starts slowing down, slowing down, slowing down. And this is slowest right here, and then faster, 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 fastest here, and then slowest here, and so on. Okay? That's how the Earth moves around the Sun. Now, why does it do that? Why does it do that? Well, we're going to talk about that when we cover gravitation. But for the time being, here is the thing. Notice that the distance between the Earth and the Sun is constantly changing. This is not a circular path. It's not a radius. Okay, look at that. The distance from here to here is definitely larger than the distance from here to here. You see what I'm saying? And of course, the largest distance is from here to there. In other words, when the Earth is here. Okay? So the reason it goes, so that when we ask the question, why does it go very fast here and very slow here? Well, it has to do with angular momentum. Let me tell you. Let's pick the Earth here and the Earth here. I'm going to call the distance between them here is, oops, I don't need this. Let's call the distance between them is R1, okay? And here is the velocity of the Earth. I'm going to call it V1. Here we're going to call the distance from here all the way here, you know, the distance from the sun from here all the way here. We're going to call that R2. And the velocity of the Earth, oops, tangential, we want it to be tangential, like this, there we go, V2, okay? Nature says that the product, okay, well, the angular momentum is L equals mvr, right? Nature says that the angular momentum at position 1, this is position 1 right here for Earth, and this is position 2, it must equal to the angular momentum at position 2. This is called conservation of angular momentum. That's the essence of angular momentum. That the angular momentum is conserved. It means the angular momentum of the Earth around the sun at any point on its trajectory is exactly the same number. Well, the only way that you can make those two the same, even though the radii, look at the radius here and the radius here, this is much shorter. The only way you can do that is that to make the speed here goes faster and the speed here goes slower, in order to make the product mvr to be the same. Make sense? So the meaning, the essence of L1 equal L2 is that m V1 R1 is equal to m V2 R2. Take the m's out, so I end up with V1 R1 equals to V2 R2. The only way that this will hold is that when R1 is small, V1 becomes big. When R2 is big, V2 becomes small. And that's exactly what's happening here. Well, that's exactly what we are observing here. Okay? Why? So when someone asks, why does the Earth goes really fast when it is at the closest point of the sun, from the sun? It's because of conservation of angular momentum. Okay? All right, good. Let me do one example and show you how this applies to what we're doing. Okay. The example is from the book, example 18. Let me look it up in my hard copy, and then I'll come back and show you. 18, page 322. So here is the conservation angular momentum. He talks about all that I have just covered for you. Please take the time to read from your book about angular momentum. This is the example that we're going to do. Okay, so you have this picture. Here it is. I'll come back to it. It says two equal masses are at the ends of a massless 50 centimeter long rod. We're talking about this one. This is the massless rod. We have two equal masses. They're going around, you know, like a dumbbell or something. The rod spins at 2 revolutions per second. Okay, so they're going, 2 revolutions per second, the rods. About an axis through its midpoint, right there. So this is the axis, so it's going around. Here is the direction of motion. That's omega, 2 revolutions per second. Okay. Suddenly, a compressed gas expands the rod. So we have inside the rod, there is gas that will cause it to expand outwards. So the M2 goes this way and M1 goes this way. It becomes longer. There we go. That's what we have. So you have a longer rod going that, though in both. And now we have a wider or a larger radius. You got that? Compressed gas expands the rod out at a length of 160. Remember, we started with 50, now it's 160. What's the rotational frequency after the expansion? Okay? So how do we do something like that? All right. It's not a difficult problem. It's very similar to the Earth and the Sun. So the initial length, well, let me draw both of them. So what I have first is, here is the initial position here. Here is the two the two masses. Here is the rod, and here is the rotation going around. That's omega 1. This is situation 1. And then situation 2, it's bigger. I'm going to make it a little bit bigger like that. I know my drawing is lousy. Sorry about that. And now we have a new omega 2 here, if you will. Okay. This is 160 centimeters. This is 50 centimeters, like so. Okay, and then we are saying that L1 is equal to 50 centimeters, that's the length. L2 is 160 centimeters, okay? And the frequency F1 is 2 revolutions per second. And he's asking for what is the second revolution here? Omega 2, basically. He wants omega 2, okay? So how do we do it? Well, first of all, you know the radius here is R1, and this is R2 here, from here to there. And of course, R1 and R2 are basically half of L1 and L2. I hope you understand that. Okay. So how do I do this problem? Simple. Just apply angular momentum conservation. So L1 equals to L2. L1 is M V1 R1 equals M V2 R2. Okay. V is not given to us, but I know that V in general is omega R. He's asking me for omega, really, okay? But I know that omega is 2 pi f, so that's 2 pi f R. So there we go. I have an expression for V, so I can use it and put it right here. The masses cancel out, so I end up with 2 pi f1 R1 squared. Remember, I have R1 here and another R1 here. So that's going to be R squared equals to 2 pi F2 R2 squared. The 2 pi's cancel out. I end up with this interesting expression. And as you can see, I'm almost done with the problem. He's asking for F2. Well, F2 is basically R1 over R2 squared times F1, right? And just plug them in. So I have here R1 is basically half of 50, which is 25, and half of 160, which is 80. I can keep them in centimeter because they're going to cancel out anyway, so I don't need to convert them. I hope you understand that. So 25 centimeter divided by 80 centimeter, quantity squared times F1, he said it's equal to, given to us, it's 2 revolutions per second. It says there in the problem. It's in the proper unit, 2 rev per second. And then we just calculate that, instead of saying. And once we calculate it, you will end up getting F2 to be equal to, let me see it. So I have here 25 divided by 80, squaring that, times 2, and that will give me 0.195. That's about 0.2 hertz, or let me just say revolution per second. Now our gas is going to slow down because it gotten bigger, correct? You know, the radius have gotten bigger. See, it was spinning at 2 revolutions per second, but the radius gotten bigger, so it has to compensate for that, so it's going to slow down. So, which is true. So we got 0.2. So from 2 to 0.2. Got it? Okay. I think this is it. I think I want to stop here. This is good enough information for this chapter. And have a good day. Bye-bye. Okay.